definitely it relates to the first law of thermodynamic, because first law of thermodynamic is explained about the law of conservation of energy. So it states that energy can neither be created nor destroyed. So in the general forms of first law of thermodynamic is, so inlet energy plus heat normally the nomenclature is Q, minus outlet energy plus work equal to accumulations. So the inlet energy and outlet energy is summations or total of all energy such as potential energy, kinetic energy, and also the internal energy. Okay, so what is the three components of total energy? The kinetic energy, so this is the explanations of about the energy. So first, the kinetic energy is the energy due to the translational motions of the system as a whole relative to the some frame of reference, usually the Earth's surface or to rotations of the system about some axis. Potential energy is energy due to the positions of the system in a potential field, such as gravitational or electromagnetic fields. Normally is MGH. Okay, the internal energy, all energy possessed by a system other than kinetic and potential energy, or energy due to the translation, rotation, vibration, and electromagnetic interactions of the molecules, atom, and subatomic particles within the system. Okay, for the system, we have two normally. First is a closed system. So for closed system, there is no mass is transferred across the system boundaries while the process is taking place. Okay, so for example, we have the batch reactor. Kalau batch reactor, there is no flow in and flow out, right? So there is no mass transfer while the process is taking place. So energy may be transferred between such a system and its surrounding in two ways, as a heat or work. So heat and work. So what is heat? So heat is energy that flow as a result of temperature differences, so delta T, between a system and its surrounding. So the directions of flow is always from a higher temperature to the low temperature. So heat is defined as a positive when it's transferred to the system from the surrounding. Normally we use the term, so the heat is positive when heat is added to the system, right? Added to the system. And then the heat will be negative when the heat is lost from the system. Okay, what about work? So work is energy that flow in response to any driving force other than temperature differences, such as force, torque, or a voltage. So work is defined as a positive when it is done on the system. So work is positive when work is done on the system. What about negative? If negative means that the work is done by the system. Very good. By the system. You have learned in the thermodynamic. Okay, now we look at the open system. So open system means that mass is transferred across the system boundaries while the process is taking place. For example, we have the CSTR. So we have inlet and outlet. Okay, string. So there is mass to the system and mass out of the system. So therefore, work must be done on open system to push the mass in the system. And work is done on the surrounding by mass that emerge from the system. Okay, so both work terms must include in energy balance for open system. The net work done by an open system is work is combinations of the work shaft plus work flow work. Okay, so the star and not and dot here means that rate of work. Okay, so what is shaft work? Shaft work normally known as the mechanical work. Right. Normally shaft work kita panggil sebagai mechanical work. So shaft work is a rate of work done by process fluid on a moving part within a system such as pump rotor. Kalau kita punya stirrer ni, this is not a shaft work. It's not, okay? So shaft work also normally also result from the external force. From the external force and also from the gravity. Meanwhile, for the flow work is a rate of work done by the fluid at the system outlet minus rate of work done by the fluid at the system inlet. Okay, so the work is pressure you times with the volumetric flow rate. So kalau kat sini untuk the inlet normally we have pressure in and kita ada volumetric flow rate in. Similar to the outlet stream. Ada P out and we have volumetric flow rate out. So that workflow here is equal to work out. So that P ada P out times with a V out minus PE volumetric flow rate in. Okay, so this formula of this equation you need to remember. So the unit is pressure is Newton per meter square times with the volumetric flow rate, so meter cubic per second. Therefore, the unit is Newton meter per second, which is equal to joule per second. That's why the rate of work lah. Okay, now let's take a look back the first law of thermodynamic in the steady state condition. So in term of rate of energy, we can set that for the first law of thermodynamic, rate of energy in minus rate of energy out plus rate of work done on system by external force plus rate of energy by productions equal to 0. 0 means that the system is in the steady state. Okay. Okay, so the energy in minus energy out, the energy here is combinations of the kinetic, internal, and also the potential energy. And then plus Q refer to the heat, and then plus W is refer to the work. Okay, so we look term by term. So Q here is due to the conduction. When I said conduction, means that it involves the Fourier law. So this is due to the molecular motion, right? So if Q over A is equal to heat flux. Okay. Okay, for the kinetic energy and the internal energy, these two terms is known as the convective energy transport. Okay, this is due to the bulk flow of fluid. Okay, kalau molecular conduction, kalau bulk flow by convective. Okay, and then the work here, we have to either the flow work or the shaft work. Okay, so combinations of the shaft work and potential energy will contribute to the rate of work done on system by external force. Okay, and then the combinations of the kinetic, internal, Q due to the conductions, and also flow work is known as the combined energy flux. Okay, And then rate of energy due to the production. So productions here means that work from other source except for the mechanical work. Mechanical work is included in the workshop. So other than mechanical work, we assume it's the production, either by the radiation, electrical, and nuclear or others. So in our syllabus, we'll cover the electrical, and also second is by the viscous heat source. We learn only two systems, okay? Okay, now we will go term by term. So for the conduction, kita akan lihat at the section 3.1, and then convections at the section 3.3, and then the rate of work done on the system by external force here. This one refer to the section 3.4, okay, which is work associated with molecular motion. Okay. Okay, now 3.1. Okay, so 3.1 is the Q, which is conduction. Due to the conduction, we refer to the molecular energy transfer. So I have said, explained here earlier, when the conduction means that we refer to the Fourier law of heat. So kalau Fourier law, now kita akan tengok how this Fourier law will be developed. It's quite similar to the momentum. Okay. Okay. So this is the diagram. So we consider a slab of solid materials, which is between the two plates. Okay. So this is the upper plate, and this is the lower plate. Okay. So between these two plates is the solid materials. So the distance between both plates is the y. So the temperature of the solid throughout this solid is T0. Okay, so this is the T less than 0 initially. Okay, so initially the solid is a temperature T0. Okay, so lower plate suddenly rise to the temperature T1. So there is temperature differences between T0 and T1. So that the temperature will be transferred from the high temperature to the low temperature. So this is high, right? So the temperature, so that the energy will be transferred to the upward because upward is low. This is high. So they akan go to upward. So the energy or the heat transfer upward. Dia akan ke atas. Okay. Therefore, as time proceeds, the temperature profile in the slab change. Dia akan berubah. And ultimately, it will achieve linear temperature distribution. So at this point, the condition is at a steady state. Okay. So as steady state condition being achieved, a constant rate of heat flow, which is Q, through the slab is required to maintain the temperature differences. Okay, so this Q, okay, but before that, if momentum, kita ada apa? To maintain the viscosity kat situ, the velocity. Kita ada force, right? Previously. So kalau untuk energy, so it required constant rate of heat flow, Q. So this Q, when we divide with the solid material area E, so it equal to the thermal conductivity times with the temperature differences divide with the distance. Okay, so this one refer to the macroscopic system. Okay, so for the microscopic system, the local rate of heat flow per unit area with heat flux Q in positive y directions is equal to negative K dt over dy. Okay, this is the temperature gradient. And Qy means that the heat flux in positive y direction. So kalau kat sini dia punya axis, this is x, this is y, lah. Okay, so dia ada at the steady state linear temperature distribution. So the slope is negative. Therefore, in order to maintain the y as a positive direction, so kita letak negative here lah, because the slope is negative. Okay, so similar. Okay, this is referred to the one-dimensional form of the Fourier law of heat conduction, one dimension. So similar to the other direction. So biasa kita akan ada Qx and also Qz, the other direction lah. So kalau Qx is equal to negative K dt over dx. So kalau negative Qz negative K dt over dz. Okay, it means that the heat flux is transferred in positive z direction. This one means that the heat flux is transferred in positive x direction. Okay. Okay. So here, x, y, and for z. Okay. So that we can write these three-dimensional form in general, which is equal to Q ball, here is a ball, equal to negative K divergent T. So Q kalau volume means that kita ada Qx, Qy, and Qz, three dimension. So this equation describes the molecular transport of heat in isotropic media. What is the meaning of isotropic media? Isotropic media means that the material has no preferred direction, so that heat is conducted with the same thermal conductivity K in all directions. So K is constant ataupun similar. Okay, so beside the thermal conductivity, the other quantity known as the thermal diffusivity is also widely used. Alpha, okay, thermal diffusivity. So this thermal diffusivity alpha is equal to K divided with the density and Cp. Cp is the heat capacity per unit mass. So the thermal diffusivity alpha has the same dimensions as the kinetic viscosity V, so which is namely length square over time. So therefore the unit is meter squared per time. So when the assumptions of constant physical property is made, the quantities V and alpha is similar with in equations of change for momentum and energy transport. So ratio V over alpha indicate a relative ease of momentum and energy transport in flow system. So this dimensional ratio is known as the Prandtl number. So Prandtl number is V, kinetic viscosity, divided with the thermal diffusivity equal to Cp mu over K. So you just substitute the formula of alpha here, then you get this term. Okay, so this Prandtl number is related to the Peclet number when you times with the Reynolds number. Okay, so the Peclet number is equal to the Reynolds number times with the Prandtl number. Okay. Okay, so example. So this is very simple example, which is to determine the thermal conductivity of the plastic. Okay, so that is as a plastic means that is a macro system. So kita tahu Q over A is equal to K delta T over Y distance. So we want to find the K, right? So rearrange the equation. K is equal to Qy A times with the delta T. So all the value of the A, delta T, Q, and Y are given. So then ada A, Y, semua dah ada. So just substitute in the equation, then you can find the value of K, which is the thermal conductivity. Okay. Okay. So because of thermal conductivity is a very important in energy balance here. So that sometimes the K kita boleh find from the experimental and also by estimation. Okay, so for subtopic 3.2, we will learn how to estimate this value K. Okay. But before that, as general, the thermal conductivity of gases at low density is increased when the temperature increase. Meanwhile, the thermal conductivity of liquid, most liquid, is decreased when the temperature is increased. Okay. Okay, now how to estimate the thermal conductivity? So we can estimate the thermal conductivity by using this figure. Similar to the momentum. Momentum kita nak estimate apa? Is the viscosity, right? So for the energy, kita akan nak estimate thermal conductivity. So this figure, you must have the reduced temperature. So reduced temperature is equal to the temperature divided with the critical temperature. And then for the y-axis is the reduced thermal conductivity. Kr is equal to the thermal conductivity of the materials divided with the critical thermal conductivity of the materials. Okay, so in the figure there is a curve here. So curve here represent the reduced pressure. So reduced pressure is P, the pressure of the material divided with the critical. This all the critical property, which is TC, PC, and also the KC, you can find from the appendix E. Okay, either you want to find from the appendix E, kalau let's say tak ada and you have data from the experimental, then you can estimate from the experimental. Okay, so for example, let's say the reduced temperature we have 5. Okay, and then the PR is 40. So the intersect between the TR and PR at this point, so that you can track to the y-axis in order to find the KR. So once KR value kita ada, then you can find the K. So K is KR times with the KC. Okay, so this KC you will dapat daripada appendix E or by the estimations on the experimental. Boleh juga. Okay. Okay, let's take a look an example. So we want to estimate the thermal conductivity of ethane at temperature and also at this temperature and this pressure. From the experimental value, the K, the temperature and pressure are given. Okay, so how to estimate this K? Okay, so kita ada daripada eksperimen data. So from this eksperimen data, kita boleh cari the KC. Instead, kita tak guna KC from the appendix E. So kita find daripada experimental data. So from here, you tengok you ada temperature, you ada pressure. So that you carilah you punya PR. This is TR. TR, then you lepas ni boleh cari PR. Okay, so TR, PR. So from here, you boleh cari you punya apa? KR. So from KR, daripada figure dapat 0.38. So you can find the KC. So KC is equal to K, you divide with the K, reduce thermal conductivity. Okay, so here even ini. Okay, so you divide dengan KR. So you dapatlah KC. So means that KC ni from the experimental, not from the appendix. Then barulah kita nak cari the thermal conductivity at this condition. So how? So ambil je lah from the kita ada temperature, ada pressure. So cari TR, then cari PR. From both here, you dapat you punya K, reduced thermal conductivity. So from the reduced thermal conductivity, you boleh cari you punya K is equal to KR times with the KC. So this KC sini, this from atas ni. So akan cari K. Okay. Simple. Okay, so any question regarding 3.2 and 3.1 and 3.2? Sebarang soalan before we proceed. Boleh? Okay, if there is no question, then we proceed to the 3.4. Okay. But before that, okay, jap. Okay, the 3.1 by conduction kita dah baca tadi. So Q is equal to negative K dt over dy. Okay, now we want to learn about the convective energy. So convective energy is combinations of kinetic and internal energy. Okay. Okay. So convective energy. Okay. So energy may be also transported by the bulk motions of the fluid. Okay, so in figure 9.7-1, we show three mutual perpendicular element of area ds at point P where the fluid velocity is V. So this is the diagram. So kita ada surface element. So this surface element must be perpendicular to the axis. So here for the x. So this surface area perpendicular to the y. And also this one perpendicular to the z. So kita ada velocity here. Okay. Okay. So the volume rate of flow across the surface element ds perpendicular to the x-axis is Vx times with the ds. So kat sini kita akan tahu volume rate of flow perpendicular is Vx ds. Dia cakap volume rate kan? So that Vx is the velocity second. So you times with the ds is the surface element. So meter square. That's why dapat meter cubic per second. So sesuailah volume rate of across this surface element is equal to kinetic energy plus the with the internal energy you times with the volume rate of flow. Okay, so this one. Okay, so this the unit is for this one. So the unit is joule per second. So but flow rate of flow energy. So energy is joule over rate over second. So joule per second. Okay. So kalau nak cakap rate of flow energy across ds pada y axis, so kita akan ada apa? 1/2 rho v plus vy ds. So for this one also 1/2 rho v plus rho energy plus vz ds. Right. Okay. Okay. If we now multiply each of the three expressions by the corresponding unit vector, instead corresponding unit vector is the delta. So ada delta x, delta y, and delta z. The corresponding unit vector is just to show the direction. The vector, to show the direction. And then we add all the three expressions. Then after that we divide by ds. So kita this one, dia kata we need to multiply with the corresponding unit vector. X. Okay, then kita plus dia kata. So dx plus y plus z. And then divide with ds. So divide, bahagikan. So mana ds? So finally, you akan dapat this term on A. This one. Okay. X, Y, and from Z. So this, in a general, we can write as the 1/2 rho V squared plus rho internal energy in bracket times with the V. So V is a pole, Vx, Vy, and Vz. So this is convective energy flux vector per unit area sebab kita dah divide dengan ds. Okay, so the unit is joule per meter squared per second. Initially tadi kita ada the unit is joule per second, right? So kita divide with the ds, so joule per meter squared second. Okay. Okay, now we look at the term 3.4, which is work associated with the molecular motion. Okay, we go back. For the first law of thermodynamic, which is conservation of energy, the change in the internal energy of the system is equal to heat added to the system plus the work done on the system. Okay. So this one, when we talk about the change in the internal energy. So delta U means that the outlet internal energy minus inlet internal energy, ataupun kita panggil sebagai final state U minus final state initial state U. Okay, ni daripada mana? Daripada kita punya first law lah. Kan first law kita ada inlet energy plus heat minus outlet energy plus work equal to 0. So kalau we rearrange balik, so kita dapat outlet minus inlet. Okay, energy. So we focus to the change in the internal energy. So that's why kita dapat outlet U minus inlet U. Sebut juga delta U. Okay. So for a flow system, source of energy transport is first heat added to the system by molecular motion. It's a Q, conduction. Okay, and then by bulk fluid motion, which tadi kita belajar 1/2 rho V plus rho internal energy, the V, right? And then second, the source of the energy is by work done on system by molecular motion. So this one known as the work associated to the molecular motion. So how this work can be associated with the molecular motion? Okay, let's take a look. So when force F acts on a body and cause it move to a distance dr, so the work done is dw is equal to force times with the distance. When we said that rate of doing work, rate, right? So kita divide with the time. So dw over dt is equal to F force times with the dr over dt. So dr over dt is the velocity. Distance divided with the time, so it's a velocity. Therefore, rate of doing work dw over dt is equal to Fv. AB ambil tu charger. Wait, charger. Bi tak boleh pun on dulu nak. Okay, boleh. Okay, thank you. Okay. Jadi, okay. Okay, apa tadi? Dah lupa pula. Okay, so this one, rate of doing work. Okay, so rate of doing work, kita ada dw over dt is equal to force times with the velocity, right? Okay. Okay, force times with the dr over dt or equal to F times with the velocity. Okay, we will consider the three dimensions. Okay, first we consider the surface element perpendicular to the x-axis to the point. Okay, so this is x-axis, so this is positive x. So definitely kita akan ada the back side is the negative x. Okay, so fluid on the minus side of the surface exert a force. So the force is exert a force on the fluid that is on the plus side of the surface. Means that the force push the fluid from the negative x-axis to the positive x-axis. Okay, so this force will make the fluid flow. Okay, makes the fluid flow. Okay, so this F is equal to pi x ds. Pi x here because the x-axis. Okay, remember in the momentum we have learned. Okay, pi is equal to what? Pi is equal to pressure times with the delta plus tau, right? Which is P here is a pressure force, tau is the viscous force. Okay, so this both force will make the fluid to flow. Okay, from the negative side to the positive side. Okay, so that we know that rate of doing work, which is F times with the V, so it is equal to, so F is a pi ds, so you buatlah pi ds times with the V. So rearrange, it become pi V x ds. Okay, so similar to the y-axis. Okay, this is y. Okay, but before that, make sure the ds must be perpendicular to the axis. Okay, so this is y. So it's a positive y. So definitely kita akan ada the negative y. Okay, so this force, the fluid on the minus side of the surface will exert a force which is pi y ds on the fluid that is on the plus side of the surface. Means that the force push the fluid from the negative y-axis to the positive y-axis. Okay, so finally we have pi v ds. So similar for the z-axis. So we have pi v y ds. Okay. Okay. So this is for the x, for the y, and for the z. Okay. So these three expressions, if we divide with the ds, kalau kita divide with the ds, dia jadi apa? Divide with ds means that you cancel lah ds ni, right? So tinggal pi times with the v. So you akan dapat pi v, okay? For x, for y, for z. So before you divide with the ds, the unit is, what is the unit? The unit is a joule per second. So bila you divide with the ds is meter square, right? So that dia akan jadi joule per second. You divide the meter square, it become joule per second. This is work flux. Okay, so combinations for the x and y and z axis, it become pi times with the v. Okay, so equal, this is apa kita panggil tadi, corresponding unit vector. Okay, just to show the direction, X, Y, and Z. Okay, so this is in general. Okay, okay, now the combinations of the Q, which is heat flux, due to the molecular, due to the convective, and also due to the work associated with the molecular motion, will known as the combined energy flux. Okay, so this combined energy flux in terms of the equations in the internal term, internal energy term. So internal energy is very difficult to measure. So normally kita akan try to convert it to the enthalpy. Enthalpy term. So how to convert? So we can convert this one by substitute the pi here. So you know tadi pi is equal to pressure times the delta plus tau. So you need to substitute this equation to the main equation here and rearrange, and finally you will get in terms of enthalpy term. How to? You try. You can try by yourself. It's a very simple, but actually it's already described here. Okay, just substitute. You substitute with the P, then you rearrange. Okay. Okay, so as a summary, we can set that for the energy, we will have first is by the molecular heat flux, Q, is by conduction. We say bila kita cakap conduction means that is a molecule, molecular motion, and then it follow the Fourier law. Okay, and then second is by convective energy, and the third one is by work associated with the molecular motion. So this is the combinations of these three terms will produce combined energy flux factor in terms of internal term or in terms of enthalpy term. Okay. So if I compare with the momentum, it's a very similar. Okay, this is for the momentum we have learned previously. Okay, first kita ada term untuk by molecular motion, which is Newton's law. Kan, kita ada molecular, so kita follow Newton's law. This one dia ada apa? Tau is negative mu dv, for example x equal dy. Okay, so kat sini kita ada Q by Fourier law molecular. So kita ada Q, for example Qy is negative k dt over dy. Then kita ada convective momentum. So here pun also ada convective momentum due to the bulk flow. And then the third one, kita ada work due to the molecular. And here also we have momentum due to the molecular. Okay, so the combinations of energy flux here. So kat sini untuk momentum kita ada juga combined momentum flux. Okay, so it's a very similar. So all of this is the fundamental of energy before we like to derive the temperature profile. Okay, so the temperature profile by using the shell energy balance, inshallah we'll study next week. Okay, any question class regarding the lecture? Sebarang soalan? question. So this week we don't have the tutorial, so you can try to understand again about the fundamental, and also don't forget about our assignment. Okay, so if you see the models, I have uploaded the assignment, so you can download and then you can discuss in your group. Okay, so hopefully you have registered your group. Dah register ke belum? Saya tak check lagi.
Dah doktor.
The due date saya bagi Jumaat ni Jumaat ni tadi tu. This week if I'm mistake. The deadline for the registration. Okay, make sure the maximum of the student in the group is 3 of you, or if you don't want 3, then you can buy 2. Okay, I'm not prefer if you do it by individual, sebab this is group assignment. So at least you remember lah. Sebab kalau you buat seorang-seorang, means that the workload pada you akan berlebihan lah maksudnya. Sebab this assignment is designed for the group, by group. Okay. Okay, that's all class for this week. Inshallah, we see again next week for the shell energy balance. Okay, thank you so much class.
Doktor tak share attendance lagi.
Oh, I see. Okay. Saya share dalam WhatsApp group boleh?
Okay.
Boleh doktor.
Okay, thank you so much.